In this video, I want to discuss the relationship between structure and polarity. In the previous course, we learned about polar bonds and about dipole moments and overall polarity in molecules, right? So we talked about, if we just take a simple example, right, something like HF, right? We talked about how this electron pair, even though it's being shared between the two atoms, because of a difference in electronegativity, they're not actually being shared equally. They're being shared unequally, and that fluorine, since it's more electronegative, is going to want to attract that electron pair a lot closer to it than to the hydrogen atom. So we talked about this idea of partial negative and partial positive charges, right? So we have a partial negative on the fluorine and a partial positive on the hydrogen. And we would call this bond a polar bond, or a polar covalent bond to be more specific, right? So it's a polar bond where the electrons are shared, but they're not shared equally. And majority of bonds fall under this category. They're not going to be shared exactly equally. They're going to be more attracted to the more electronegative atom. And so when we start talking about three-dimensional structure, we can start to talk about the directionality of the polarity, right? So for example, in this case with HF, we could draw a dipole moment, arrow, and we know that the dipole would be facing the fluorine since the fluorine is more electronegative, right? So same thing with three-dimensional structures, but now we have to talk about that direction in 3 dimensions, right? So let's take a really simple example. Let's take the water molecule and look at what we can say about its polarity and the direction of the dipole moment. So for the H2O molecule, right? So again, we have H2O, 2 hydrogens, 1 oxygen. The oxygen is going to be the center atom. So it has a Lewis structure that looks like this, right? Where you got 2 lone pairs on top of the oxygen. Okay, so if we're calculating a steric number here, our oxygen is going to be the central atom. So if we're calculating the steric number, we're going to have 2 bonds, 1 to each hydrogen, 2 bonded atoms, plus the 2 lone pairs here. And that's going to equal a steric number of 4. Now, if you look at your chart, when you have a steric number of 4 with 2 lone pairs, that's going to give you a bent structure. So water is going to have the following 3-dimensional structure. I'm going to give myself a little bit of room here. Right, so we got hydrogen there, hydrogen there. Right, so it's going to have this bent structure where the electron pairs at the top are taking up a lot of space and they're bending those bonds to the hydrogen downward. So this is going to be the 3-dimensional structure for water. Now, what about its polarity? Well, we know that both of these bonds are going to be polar bonds, right? So you're going to have a partial positive at each individual hydrogen and a partial negative at the oxygen atom, right? So when we talk about the directionality of the dipole, right, we know we're going to have, a bond dipole that points this way here and a bond dipole that points this way here, right? And so what we can start to talk about is the overall direction of the dipole moment for the molecule, right? Since these are both pointing upwards toward the oxygen, we can have a total molecular dipole moment that's pointing this way, right? So you can think of this how you might think about vectors in algebra, right? The 2 vectors are kind of, in a direction where they're adding together. And so they're going to form a molecular dipole that points in this direction with respect to the framework of the water molecule because of the direction of these 2 bonds. So we can start talking about the directionality of this polarity. Right, now let's look at another example here. And the example I want to look at is xenon XeF4. Right, classic example, really cool story behind this. Noble gases thought to not react with anything, and somebody won a Nobel Prize by reacting xenon with a bunch of halogens, and the rest is history. But that's the XeF4 molecule. So for XeF4, it has the following Lewis structure. I won't go through all of the details here, just because I really want to focus on the polarity conversation. But as the following Lewis structure. So, of course, we got lone pairs around our fluorines. And we still have 2 lone pairs that are outstanding here. And so we put those on xenon. Xenon is well below period 3, and so it has those close by d orbitals in order to accommodate more electron pairs. So it's happy with this expanded octet. So that's our Lewis structure. So now we want to calculate a steric number. All right, so we calculate a steric number. Steric number, we're going to have 4 bonded atoms here with each fluorine bonded to the xenon. And that's going to be 2 lone pairs. So it's going to give us 6. So if you look at the table, when you calculate a steric number of 6 and you have 2 lone pairs on the central atom, that's going to give you a square pyramidal structure, right? So basically it's going to be a square with xenon at the center of the square, right? So I'm just going to draw these here without the lone pairs present. Okay, so if we investigate these just on the individual bonds, right, we're going to have polar bonds all around. Fluorine is much more electronegative than xenon, so we're going to have a partial negative at each of these fluorines, right? And so for each of these, and I'll put a partial positive here at xenon, right? So all of these are going to be polar bonds. They're going to favor the fluorine, right? So, so we're going to have polar bond dipole here, polar bond dipole here, polar bond dipole there, polar bond dipole there, right? So we got polar bonds all the way around. But I want you to ask yourself, do we have a total molecular dipole? And if so, what direction is it pointing in? So what I wanted to drive home with this example is that you can have molecules where you have polar bonds, but there is no overall polarity for the molecule. There's no overall net dipole. And this is the perfect case because you have all these bond dipoles are going to cancel each other out, right? You see that this is going in the exact opposite direction of this one. This fluorine bond is going, the dipole is going in the exact opposite direction of this one, right? So we actually won't have an overall molecular dipole here for xenon tetrafluoride because all of these dipoles are going to cancel out. And that is a direct consequence of the shape of this molecule. Since it's square pyramidal, these dipoles are pointing in the exact opposite direction of one another. And so we don't have a net molecular dipole, right? So this is going to be, this is always going to be situation dependent, right? Depends on what your molecular geometry is, and if you have all the same molecule, all the same atoms involved in the bonds. So for example, and this is just an example, so this isn't a real molecule that's been created, right? But let's say hypothetically we replaced one of these fluorines with a chlorine, right? We would still have this polar bond here, right? So it would still be more electronegative than xenon, but it wouldn't exactly cancel the dipole on the other side because it's a different atom, right? So you would have a net molecular dipole in this case, but if we go back to our original example of xenon tetrafluoride, right, this guy is not going to have a total molecular dipole because it's going to exactly cancel out on all sides. So whenever you're trying to investigate whether a molecule will have a total molecular dipole or not, you have to consider the three-dimensional geometry. It's not enough to just look at the Lewis structure because it could be misleading as far as whether something has a total molecular dipole or not. Okay, so that's a little bit on the relationship of molecular structure and polarity. So they have this interplay where you need the three-dimensional molecular structure in order to figure out if a molecule is polar.